Well, welcome to Lecture 4. And what we're doing is we're moving past electrical energy. You've had a few lectures on basic electricity concepts, basic power ideas, and then moving into three-phase power. What we're going to do now is start on a different tack, looking at the thermodynamics of energy conversion. And so we'll proceed with this. Can you get the door for me? Thanks. Okay, so first of all, what we're going to do is start looking at basic definitions and energy units. We'll go through the first law of thermodynamics, talk about vocabulary, internal energy, work, heat, and enthalpy. Then we'll get into the second law of thermodynamics, thermodynamic properties. Then we'll talk about some thermodynamic cycles and finish up talking briefly about energy content in fuels. So, definitions of entropy. And these are definitions of thermal energy based initially on the properties of water. For instance, 1 calorie is the energy needed to raise 1 gram of liquid water by 1 degree C. So you've got a beaker, you put in a measured amount of water, you add heat until the temperature goes up 1 degree. Okay? Well, this is the definition of a calorie. And I should also mention at this point that if you look on, for instance, a food package and they talk about the number of calories in a candy bar, that's actually kilocalories. That's the amount of energy required to raise a kilogram of water by 1 degree C. 1 British thermal unit is similar, except it's defined in the English system. It's the energy needed to increase the temperature of 1 pound of liquid water by 1 degree Fahrenheit. We will tend to use BTUs rather than calories. Calories are typically used more in chemical analysis. However, the study of thermodynamics really took off when it was discovered that there is a mechanical equivalence of heat. For instance, we can also define energy as force acting through distance. That's typically how we would define work. But there is an equivalence between thermal energy and mechanical energy. Now you can see this in one direction. If you rub your hands, the mechanical energy turns into thermal energy. However, what we're looking at is energy conversion such that we can take thermal energy and turn it into mechanical energy. That turns out to be a little bit more challenging. Now, what we're going to do is we're going to work both in the English system of units and we're going to work in the SI system of units. 1 joule is, again, it's force times distance, just like foot-pounds, except it's 1 Newton meter. In electrical energy, it's 1 volt times 1 coulomb. So the nice thing about a joule is that it's consistent between mechanical, thermal, and electrical energy. We're going to look at some conversion factors here. 1 BTU is almost equal to 1 kilojoule, not quite. It's about 6% off. 1 BTU is equal to about 1.055 kilojoules. And then something else that we've already seen on some of our, for instance, introductory slides is 1 quad. 1 quad is equal to 1 quadrillion BTUs. That's 10 to the 15th BTUs. So again, this is a somewhat non-standard way of talking about energy. However, if you're talking about energy on the national scale or international scale, very often that data will be reported in quads. Okay, definitions of power. Power is energy in motion. 1 watt is a joule per second, which is a volt coulomb per second. A coulomb per second is an amp. Okay. 1 horsepower is equal to 550 foot-pounds per second, or 746 watts. If we multiply power by time, we get energy. For instance, if we take kilowatts, which is a joule per second, and multiply by the number of seconds in an hour, we get a kilowatt hour. So this is a unit of energy, and it is defined as 3,600 kilojoules, or 3412 BTU. So these are conversion factors that we will end up using a lot. Now, something that we may have touched on previously is the economics of renewable energy. Typically, when we're building a power plant, we install power, we install capacity in terms of megawatts, and this is, for instance, the capital cost. However, what we sell is energy. Okay, so we'll get more into this when we start talking about renewable energy economics a little bit later on in the semester. So basic units of the powers of 10, primarily in the SI system. Some of these are a little bit non-standard, but they're used overseas. For instance, like a deciliter is a tenth of a liter. You use this like on cooking instructions, whatever. But what we're going to be focusing on here are primarily these here, which is powers of 10, which are prefixes to the units in the SI system. If you're working in the English system of unit, you should be aware that 1 MBTU is actually 1,000 BTUs, and 1 MMBTU is actually 1,000,000 BTUs. So that's it. It's not the same as these units up here. Okay. Some more useful energy. 1 quad is equal to about 1.055 exajoules, where an exajoule, if you look on the previous slide, that's about 10 to the 18th joules. Now, you'll notice some of these other conversion factors have to do with the heat content of a certain fuel. For instance, 1 ton of coal is 25 million BTUs, or 22 gigajoules. So sometimes you'll see energy conversion done in tons of coal or barrels of oil. The amount of energy in 42 gallons of oil is 6 gigajoules. And so here, what we're talking about, this energy unit is defined in terms of the heat energy released when you burn a given quantity of that fuel. Okay. So 1 ton of oil equivalent is 42 gigajoules, which is about 39 million BTUs. Okay. So you can see that you can do any number of conversions. Now here, this one is tricky. 1 ton of oil equivalent is equal to 11,630 kilowatt hours. That's just a unit energy conversion. Okay? But that doesn't mean that if you burn a ton of coal, you get out that much electricity. That would only happen if your power plant was 100% efficient. So we have to be careful about converting energy units based on the heating content of fuel to things that imply electricity. Okay, we have to go through an energy conversion process, which is what we're going to spend quite a bit of time today talking about. So this is an example. This is an older slide. It's an oldie but goodie, which I like because it really shows the idea of conversion efficiency. And so now, if you actually look at this slide, this is actually electricity flow in quads. Okay, but what we're looking at is just the width of the various arrows. So this is from 2007, so this was coal. Natural gas is actually nowadays a much larger fraction. Nevertheless, here are the various sources of fuel that are used nationally. Here's the electricity coming out and how it's used. Residential, commercial, industry. These are all conversion losses. You see that? So this is a sense of our national electricity energy conversion efficiency. Most of this energy is actually in the form of losses. So all of this energy from here to here, that's the only amount that's actually turned into useful electricity. Okay? Now, what we'll see as time goes by is there are ways that we can possibly use some of that energy. For instance, this energy is coming off in terms of heat. Now, very often we can use this heat in a different way, and sometimes this heat is at a high enough temperature so we can actually generate more electricity with it. But these are just national statistics, but they show you the difference between the energy coming in and the energy actually that leaves as electricity. So we're going to talk a little bit about energy conversion. So this is a slide. This is from the Chicago Columbian Exhibition in Chicago in 1893, back when I was in grade school. And so this was this huge 2,000 horsepower Alice Corliss steam engine. Okay, this was the latest generation. All the workers that maintained this were in white uniforms because this particular steam engine used the fuel of the future. It did not run on coal, which was dirty and problematic. It ran on oil, which was perceived as the fuel of the next century, which indeed oil was. Well, now, here we are, 100 years later, and we're looking at alternative forms of energy to replace oil. You see how it comes and goes. Now, that being said, it's kind of nice that we have this diagram here, because you can actually see here's the cylinders, turn this flywheel, okay, that actually spins the generator. So this is actually a useful diagram. I'll be right back. There we are. Had to make sure I had enough energy to make it through the lecture. Somebody unplugged my computer. Okay, so that would have been a useful object lesson. So, energy conversion. How do we convert heat energy to electrical energy? So you could think of this as a model of this big steam engine, where we have heat added to a fluid in a cylinder. The piston moves, which creates some kind of shaft horsepower, which we can then use to spin a generator, which generates, and in this case it's three-phase power, your old friend. Okay? So what we're going to focus on is what's happening in here. We're adding heat to something, and that something is expanding. So in general, this is going to be some kind of a working fluid. It could be water, which of course turns to steam, or it could be air in a general case. So we're looking at what is inside this box. This is really the thermodynamics of energy conversion. And then this is how, this piston in this case, is how we capture that energy and turn it into some kind of mechanical energy. So this is what's inside the dotted line. This is the first law of thermodynamics. And what we have here is a system, which could be the working fluid in the cylinder, and it is surrounded by the system boundary. And I'm adding heat and extracting work, and it is possible then that this working fluid also has some change in internal energy. So the change in internal energy of a system is equal to the heat added minus the work done, because you can't create or destroy energy. It can only change from one form to another. So the internal energy is a property of the system. The heat and work are energy in transition across the system boundary. So we can write it in this form, and by convention, we would say that the heat added to the system is positive, and the work done by the system is positive. Okay? Now, for mechanical processes, you can treat the work as force times distance, or you can write it as the integral of the pressure times a differential change in volume. The idea of an expanding cylinder against a piston creates work. Where does internal energy come from? Well, it comes from the motion of atoms and molecules. For instance, the motion can be translation, it can be rotation, or it can be vibration. So essentially, internal energy is the kinetic energy of the molecules themselves. So let's talk about this in a little bit more macroscopic detail. We're going to look at two specialized systems. One is a constant volume system. So if you've got a constant volume system, there's no change in volume, and if our work is equal to the integral of P dV, if dV is equal to 0, this implies that the work is 0. So then the internal energy is just U2 minus U1. Okay? We can also have a constant pressure system. And for a constant pressure system, again, if I've got work is equal to P dV, for a constant pressure system, we can pull the pressure out, and it is just the integral of dV from 1 to 2, that's the pressure pressure times V2 minus V1. We can separate those terms and define a new variable called enthalpy. Okay, which is U plus PV. So for a constant pressure system, the heat is really the change in enthalpy. So we will very often work with things that we are assuming are constant pressure systems, and in those cases we will write the heat transfer as enthalpy. Okay. Well, we can tie this idea back to specific properties. Now we mentioned, for instance, that 1 BTU is the amount of heat it takes to raise 1 pound of water by 1 degree Fahrenheit. What that means is that water has a certain specific heat that defines how the temperature changes with energy. And we can either define that as a specific heat with constant pressure, and you could write it as a partial derivative as follows. CV is equal to du dt, or CP, specific heat at constant pressure, is really dH dt at constant pressure. So these are specific heats, and we'll look at these in more detail. Specifically, as it were, we're going to look at the specific heat of water and the specific heat of air to talk about, as we add heat to air or water, how the temperature changes. Now, what we've talked about so far are the temperatures scales, degree Fahrenheit, degree C. However, thermodynamically, a more useful temperature scale is a temperature scale based on absolute zero, where absolute zero is minus 273 degrees C or minus 460 degrees Fahrenheit. And so if you want to convert between the two, you just add the required number. For instance, the boiling point of water at 1 atmosphere, and this is important, we'll talk about this a little bit later, is 212 degrees Fahrenheit. If I want that in degrees Rankine, you add 460, it's 672. SI system of units, 100 degrees C plus 273 is 373 kelvins. Now, a kelvin is a unit, just like a joule or a watt. So you see, you don't write degrees Kelvin, it's kelvins. Okay, that's a fine detail, but just pay attention to that, because you'll very often see 373 kelvins. Okay. Now let's talk about specific heat values. Now, water has a specific heat of 1 BTU per pound degree Rankine, or 1 calorie per gram Kelvin. You'll notice that these are written in terms of absolute units. Okay? This is, in fact, the information that I showed on the first slide. This is, in fact, the definition of a calorie, and a BTU is because there's a 1-to-1 correspondence here. 1 pound of water heated by 1 degree Fahrenheit means that 1 BTU was added. Okay. Well, the specific heat of water, for instance, if we're talking the SI system, is 4.2 kilojoules per kilogram K. For air, CP is 0.24 BTUs per pound degree Rankine, or 1.006 kilojoules per kilogram Kelvin. So here's how we would use this, for instance. Determine how much heat is required to increase the temperature of 15 kilograms of water from 15 degrees C to 70 degrees C. So you would take CP, which is in kilojoules per kilogram Kelvin, and you would multiply by the number of kilograms. Now here, you can see I'm finessing the units here. This is in degrees C, this is in Kelvin. Can we do that? Can we cancel those out? Well, how would we convert these to degrees Kelvin? What would I do? Yes?
Would you have to convert them because they're on the same scale, so would the temperature difference be the same?
Well, I would add 273 to this one, and I would add 273 to this one, and then it would just subtract off, because the size of a degree C is the same as the size of a degree Kelvin. So as long as you're talking about temperature differences, you don't need to convert. However, what we'll see in a few minutes, we're going to talk about the ideal gas law. You have to be in absolute units, because there you're talking about temperature ratios, for instance. Okay? But as long as you're talking about temperature differences, you can in fact cancel these out. Okay, and what you're left with is 3465 kilojoules, or 3.47 megajoules. Okay, everybody see that? Okay, now for flow systems, okay, we look at the mass flow rate. Okay, and so dq dt, which is in units of energy per second, for instance, you'd have q dot, which is dq dt, is equal to m dot cp t2 minus t1, where m dot is a mass flow rate. So here you have water, for instance, or some kind of fluid flowing through a pipe. You have thermal power coming in, and you've got an initial temperature and a final temperature. And since we're adding heat, T2 is greater than T1. So this is an example of a flow system. Okay, so here we're actually getting into some actual renewable energy. So this is a geothermal power plant at Hetlashede, which provides district heating, or it supplies hot water for the city of Reykjavik. And the water is at a temperature of 83 degrees C, and then it's used in Reykjavik, and then the base temperature, when it's no longer considered hot water, is 30 degrees C. We want to figure out the thermal power in this water here. Okay? And we're given the flow rate is 1,800 liters per second. So the mass flow rate is 1,800 liters per second. 1 kilogram, the density of water is 1 kilogram per liter. So it's actually 1,800 kilograms per second. The thermal power is then 1,800 kilograms per second times 4.2, this is our specific heat of water, kilojoules per kilogram K. Temperature difference is 83 C minus 30 C, and you can see that we cancel out the temperature cancel out the kilograms, and what I'm left with is kilojoules per second. 401 times 10 to the 3 kilojoules per second, or 401 megawatts thermal. Okay, that's the thermal energy supplied by this geothermal power plant. Here's a reversible process, and what we're doing is we're adding heat, making pasta. And so as we add heat, gradually we increase from a liquid to a saturated mixture, and then finally to a saturated vapor. We can look at steam property tables. I'll show you some examples of these, and we can determine the enthalpy required to actually do this liquid conversion at 1 atmosphere, okay, at 100 degrees C. And we can also measure something called the entropy. And the entropy we can think of as a measure of the heat transfer that's being added. This is how many kilojoules per degree Kelvin. Okay, now, the steam properties vary with pressure. For instance, at low pressure, cooking at high elevation, so here's some kind of a mountain cook stove, at an elevation of, for instance, 22,110 meters, which happens to be the highest point in Iceland. The pressure is 78.4 kilopascals, the atmospheric pressure, instead of 101 kilopascals. So food cooks more slowly, and it actually takes more energy. At high pressure, for instance, at 2 atmospheres, here in this pressure cooker, our boiling temperature is 120 degrees C. Food cooks faster, and you can see that it uses less energy. Okay. So we can start to put all this together by looking at something called a vapor dome. And so what we have are various pressures, and then the horizontal line here is entropy. So I've got temperature versus entropy. And then we can look at various properties. For instance, along this constant pressure line, we're at 100 degrees C. If we're up to 8 atmospheres, we're at 170 degrees C. 30 atmospheres, we're at 240 degrees C. And if we've got critical conditions, this is 221 atmospheres at 374 degrees C. So for a reversible process, our second law of thermodynamics becomes an equality where the heat is really equal to the temperature times the change in entropy. This is kind of analogous to the pressure times the change in volume. The entropy is the integral of the temperature, or the heat transfer is an integral of the temperature times the change in entropy. If we're at a constant pressure process, not there. No, I don't want to see this. Okay. If we're at a constant pressure process, the heat transfer is equal to the temperature times the change in entropy. So for a pressure at 1 atmosphere, you remember that for our boiling pot of water, we had 6.05 kilojoules per Kelvin. If I multiply by the temperature at 100 degrees C, 373 Kelvin, you get 2257 kilojoules, which is the amount of heat that was added. Okay, so there's a relationship between entropy and heat transfer. Okay, we will use this particular relationship again when we start talking about thermodynamic cycles. So you can get power from steam by generating steam 2 different ways. Now, when you're getting power from steam, what you're doing is you're expanding steam through a turbine, but you can get the steam 2 different ways. One way is to start with cold, low pressure water and add heat. So this would be in a conventional boiler where the heat would come through burning some fuel. Okay, so this is the thermodynamics of energy conversion when you're burning a fuel to add heat and then expanding the steam through a turbine. However, you can also start with hot, high-pressure water, lower the pressure below the boiling point at that pressure, and it will flash to steam. This is how geothermal power plants work. You start with hot, high-pressure water underground, you bring it up, reduce the pressure, and it becomes steam. So this is a conventional power plant, this is a geothermal power plant. Now typically with a geothermal power plant, what you do is you then end up with a saturated mixture and you pull off the liquid and use only the dry steam through the turbine. But we'll have a whole lecture on geothermal power a little bit later on. This is an example of a thermodynamic cycle. And so the idea of this cycle is you've got heat coming from a high temperature reservoir to a low temperature reservoir. And these reservoirs are large enough so that as we remove heat or add heat to the low temperature reservoir, the temperatures don't really change. That's the definition of a reservoir. And as this heat is naturally falling from high temperature to low temperature, we're going to pull off some work. Okay. What's actually happening inside this little box is we're adding heat to a working fluid and changing phase from a liquid to a vapor. We're expanding the vapor with some power cycle and then condensing the vapor down to a liquid, increasing the pressure of the liquid, and so then the working fluid goes throughout these four processes. And the whole idea is that I'm adding heat. Some of that heat is going to the work of the cycle, and some is coming out the bottom of the cycle as waste heat. And so here is the idea of our energy conversion, just like I showed you. These are our conversion losses. This is the useful energy. This is the amount of heat we're adding. Well, we can talk about the efficiency of a cycle by dividing the useful work out by the energy, or by the energy coming in. Yes?
Can you take the waste heat and reuse it for the heat addition?
You really can't, because this is happening at a high temperature and this waste heat is at a low temperature. And you can't get low temperature heat back up here. You would be asking you'd be asking the heat to flow uphill all by itself. It's like saying if I've got a dam downstream of the spillway, why can't I use that water in the dam, to generate electricity? Well, it's downstream already. You'd have to pump it upstream. Okay, so this heat is at a lower temperature, and it can't go back up here. Now, what we'll see is for some gas turbine engines, this low temperature may still be a very high temperature, and we may be able to use this heat in another cycle downstream. That's called a bottoming cycle, but we'll get to that later on. I'm not going to talk about it now. We've got plenty to get through our slides for today. Now, these are statements of the second law of thermodynamics, and they have to do exactly with the question you asked about, does heat spontaneously flow uphill? And the answer is no. Heat goes from high temperature to low temperature. So that's a statement of the second law of thermodynamics. Another consequence of the second law of thermodynamics is you cannot have 100% efficiency. There will always be some heat rejected to the surroundings. Always. Okay? So you can't get to 100% efficiency. Okay? And so entropy is a thermodynamic property. You can see here is that change in entropy is equal to a change in heat divided by temperature. This is for a reversible process. For an irreversible process, the entropy change is always larger than the heat transfer divided by the temperature. Okay, so let's talk a little bit about the the ideal gas law. This is equal to pressure volume is equal to the number of moles times the universal gas constant times temperature, where RU is given here, 8.314 joules per mole Kelvin. Pressure and temperature have to be in absolute units. Okay. Now, what you could do, and very often we do this in thermodynamics, is you actually calculate a different gas constant for each gas, and you do that by taking the universal gas constant and just dividing by the molecular weight of the gas. Okay. And this is how we would do it. This is an example. Compute the density of methane at normal conditions, where normal conditions are given at 0 degrees C and atmospheric pressure. Now, the first thing we're going to do is find an ideal gas constant for methane by dividing by the molecular weight of methane. So this is now 0.5183 joules per gram Kelvin. The density here, if you look at the ideal gas law, oops, this is not going to work anymore. Okay, which is, let's go back to the previous page. PV over MRT. If you divided mass by volume, you would get rho, which is going to be P over RT. Well, we take the pressure and we divide by the ideal gas constant. And here what I did is I wrote 1 joule as 1 Newton meter. And what you can see there is that the newtons cancel out, and what we get is grams per meter cubed, 716 or 0.716 kilograms per meter cubed. This is an example of thermodynamic properties of steam. So this is essentially a numeric representation of the vapor dome that I showed you earlier. This is some superheated properties. We're not going to do a whole lot with these properties in this class. I'm not going to have you going to these tables, but the whole idea, when you're dealing with steam properties, you cannot use the ideal gas law. You have to look them up from these property tables. Okay? So here's another example. This is in the English system of units. Okay, so you've got your critical point is 705 degrees Fahrenheit, 218 atmospheres. And again, as we go to different temperatures, you can see at 8 atmospheres, you're at 340 degrees Fahrenheit, 1 atmosphere, 212.2 atmospheres, down to 141. So you can work either in SI units or English system of units. Here's an example again in the English system of units of isothermal heat addition. Okay, and a change in entropy. Okay, and again, so this is an example very similar to the one we did in the SI system. This just shows the English system of units. This is an example of a reversible process. What we have here is an isentropic expansion, which means constant entropy. So we're starting with the superheated steam, and we're coming down here to a saturated mixture. But you'll notice since S2 is equal to S1, this process is reversible. The best of all possible cycles is one in which each of the processes are reversible. So when we were looking at our boiling spaghetti, we noticed that heat addition at a constant temperature is reversible because we're basically changing phase. And if we have isentropic expansion and compression, this then, on a temperature entropy scale, is the best of all possible thermodynamic cycles. So what we can do then is, for this reversible cycle, we can write that QH over TH is equal to QL over TL. The thermodynamic efficiency we can write as work over QH, applying the first law. This turns into 1 minus QL over QH. Well, I can then get a heat transfer ratio, And using the second law, I can take this, QH minus TH, QL over TL, I can turn this into a temperature ratio. So for a reversible cycle, the Carnot efficiency is 1 minus TL over TH. However, this only works if you're in absolute units. Okay, so you have to be either in degrees Rankine or Kelvins. You can see here that for a constant TL, heat rejection to the surroundings at, for instance, 15 degrees C, the larger TH is, the higher my theoretical efficiency. So when we're looking at energy conversion processes, the higher our maximum cycle temperature, the higher the maximum efficiency is. Okay, now, we don't actually build Carnot cycles for a few reasons. Number one is it's difficult to compress a saturated mixture just like this. So typically what we will do is we will condense our mixture all the way down until it's a saturated liquid and then compress from there. Also, this is a very high moisture content steam condition here at the turbine exit. So typically what we will do is superheat the steam so that when we condense it, it has a moisture content less than 10%. So this is a simple Rankine cycle. And so what we're doing here is we're actually pumping liquid water, and then we're adding heat in the boiler from 2 out to 3. And here we're not superheating yet, so we're still coming down to 4, which is still a fairly low vapor quality of steam. There's a lot of moisture in that. Now, for a heat rate, let me explain what a heat rate is. It's like efficiency upside down. So for efficiency, normally what we're doing is we're looking at the amount of useful energy divided by the energy we're putting in. A heat rate is the amount of heat that it takes to generate a certain amount of electricity. The important thing about heat rate is that it is not unitless. And it will typically be in kilojoules per kilowatt hour or BTUs per kilowatt hour. And the higher the efficiency, the lower the heat rate, because they're basically reciprocals. So here's an example of thermal efficiency and heat rate. So we've got 1,000 kilojoules per second coming in, or 1,000 kilowatts. Of that 1,000 kilowatts coming into this thermodynamic cycle, we're getting out a useful work of 352 kilojoules per second. So we want to calculate the efficiency and the heat rate. Our high temperature reservoir is at 600 degrees C and our low temperature reservoir is at 20 degrees C. From our first law, we can get what QL is. QL is equal to 100 minus 352 is equal to 648, because the energy into the cycle is equal to the useful energy minus the thermal losses. The thermal losses are 648 kilojoules per second. The efficiency is going to be the useful energy divided by the energy we're adding, which is 35.2%. We flip that over to get the heat rate. The heat rate is actually 10,230 kilojoules per kilowatt hour. We can look at the change in entropy for this process. The loss in energy entropy from the heat source is equal to minus 1146 kilojoules per second Kelvin. The heat gain by the heat sink is 2112. The change of entropy for the cycle is 0, but the total change in entropy includes the heat source and the heat sink, which is a positive 1066 joules per Kelvin per second. So that's the net change in entropy, even though the cycle, the change in the cycle itself is 0. So Now what we're going to do is we're going to look at the best possible thermodynamic cycle acting between those two temperatures. So we take the 600 degrees C, convert it to Kelvin, 15 degrees C, convert it to also to Kelvin, and we see that our maximum Carnot efficiency is 66%, so that's almost twice what the previous efficiency was. You see that? And so the maximum power that we're getting out is 664 kilojoules per second, and we're only rejecting 336 kilojoules per second. The change in entropy you see from both the heat source and the heat sink are now exactly the same, so there is no change in entropy to the surroundings. Okay, so this is the best of all possible cycles. It results in no entropy change. So we're going to look very briefly here in our remaining few minutes at the energy stored in chemical bonds. This is different than internal energy. Internal energy was basically the energy stored in kinetic energy of molecules. Energy stored in chemical bonds is released when you take and you create new compounds. For instance, when you take oil or coal and you take that coal and you convert it into ash and CO2 and H2O, you're breaking and forming new bonds, which results in a net release of energy. Okay, so the enthalpy of formation is what we need to actually calculate this, because each type of bond has a certain enthalpy of formation. Okay, the standard enthalpy of formation is the enthalpy change when all reactants and products are at their standard states of 25 degrees C and 1 bar. And by definition, the standard enthalpy of formation of the most stable form of any element is 0. So since we're always talking about the change in enthalpy, we can just set the ground state as follows. So here are some enthalpies of formation. And so here you can see some various fuels. Propane, methanol, methane, hydrogen. So those are fuels, and then the products of combustion include carbon dioxide, carbon monoxide, and water. And what you'll notice here is that water has a different enthalpy of formation depending on whether it's a gas or a liquid. And so this is actually going to become important in a minute or so when we start talking about the exhaust. So here's methane combustion. We've got some methane, which is natural gas. We're going to burn this natural gas and see how much energy we get out. Now let's say that we don't know how much energy is released when methane is consumed, but we know the enthalpy of formation of all of the compounds involved in this chemical reaction. So there's 1 molecule of methane, and what we're doing is combining it with the oxygen to get carbon dioxide and water. And the water in this case is going to come off, we're assuming it's coming off as a gas. We have to balance this chemical reaction, first of all, by counting carbons. I've got 1 carbon on this side, so I need 1 molecule of CO2. And then we look at the number of hydrogens. I've got CH4, so I need 2 waters. And so I've got 1 carbon dioxide molecule, 2 waters, and then I start counting up the oxygens that I need over here. So I need 2 molecules of oxygen for every molecule of methane, or 2 moles of oxygen for every mole of methane. Okay? So then what we do is we go back to the previous slide and we look up all these values and we substitute them into our equation, and we see that the change in enthalpy for this reaction is minus 802 kilojoules per mole of fuel. And this is a negative sign, which means that heat is released. Now, the heating value, specifically of a combustion reaction, starts with the reactants at a standard state. We allow the reaction to occur, just like is on the previous page, and we allow the products to return to a standard state. And then we track the change in enthalpy from the final state to the initial state. Okay, so this is, for instance, the lower heating value. This is our reaction. So we've got methane gas and oxygen coming in. It releases, as we said, 802.3 kilojoules per mole. And then we've got water vapor at 25 degrees C. So this gives us minus 802.3 kilojoules per mole. The lower heating value is actually what we're going to do is multiply by the molecular weight. And so then instead of talking about kilojoules per mole, we can talk about per mass. And so we convert that to megajoules per kilogram. It's about 50.02 megajoules per kilogram. At normal conditions, for instance, we could also talk about megajoules per meter cubed. And actually, methane is actually sold by the therm, which is 10 to the 5th BTUs. It's the amount of energy in 100 cubic feet of methane. So methane is actually sold by a volume. Okay. Now, the higher heating value is if we take this water vapor and actually condense it to a liquid water, we get out an extra 44 kilojoules per mole of water. Now, where does that come from? Well, if we go back to our table here, you can see that if we've got water as a gas, it still contains 188.8, or no, it's here, 241.8 kilojoules per mole. Liquid water has 285.8, so the difference between these is 44 kilojoules. So theoretically, there's still heat that we could get out. Okay, and so in order to account for this, instead of using 241.8, we use 285.8, and you can see that the reaction goes up to 890.6. So this is a higher value. Than the 802. You see that? So the lower heating value was based on the enthalpy change of 802. This higher heating value is 890. Okay, so there's more energy in the fuel. The challenge is that there aren't many pieces of equipment that actually condense the water to get that energy out. For instance, for instance, if you're driving your car, the water comes out the tailpipe in terms of vapor. Same thing here at the steam plant. Even with the boilers that are burning natural gas instead of oil, the water comes out as water vapor. So this energy is usually left on the table. The higher heating value of methane is, again, it's about 39.75 megajoules per meter cubed. And here's what I was saying earlier. At standard conditions, the higher heating value of methane is about 10 to the 5th BTUs, 100 standard cubic feet of gas, where a standard cubic feet of gas is measured at 60 degrees Fahrenheit and a pressure of 30 inches of water, which is about 1 standard atmosphere, more or less. So you can see here different types of fuels. And here, the units on this are kind of vary a little bit, but you can read down the columns. This is energy per unit mass. And so you can see on a per unit mass basis, hydrogen has the highest energy per unit mass of any fuel. Okay? However, it has the lowest energy if you're looking at energy density in terms of volume, because it's very hard to store hydrogen, the highest energy density is actually diesel. That is the most dense fuel that we have. So this is an example of higher and lower heating values to get back to the idea of, are there any devices which actually enable us to recover that water vapor condensation? And it turns out there are. This is a conventional multi-fuel boiler. This can burn either natural gas or oil, and the efficiency is about 83%. The stack temperature is quite high. It's 370 degrees Fahrenheit. And it needs that high stack temperature because of, for instance, the sulfur, which could be present in liquid oil, and you don't want moisture condensing in your exhaust if you've got sulfur, because you can form sulfuric acid. Okay. This is a condensing boiler. This only runs on natural gas. The stack temperature is 104 degrees Fahrenheit. It's about the same as a dryer vent. But you also have to plumb a water exhaust, because most of the water comes off as liquid water. But you can see you have much higher efficiencies, because this boiler actually it doesn't do it in two processes, but actually you get out that additional higher heating value benefit. Okay. All right, so that is a fairly rapid review of basic thermodynamic concepts, and we will, throughout the next few lectures, go through, look more in detail at steam power plants, and we'll also talk more about gas turbine power plants as we go. We'll also come back and revisit some of the stuff on fuels later on. But this is just a kind of a review just to get us started. So thank you for your attention.